This video is for topic 6.8, or the enthalpy of formation. And the objective for this topic is to calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation. So enthalpies of formation, standard enthalpies of formation, are similar to our standard enthalpies of reaction, but in this case it's delta F instead of delta R, H naught. So this is the enthalpy change for the formation of 1 mole of a compound directly from its component elements in their standard states. So that's the form that those elements are in at roughly room temperature and 1 bar of pressure. These formation reactions don't necessarily correspond to something that you can actually carry out in lab. This is kind of a simplified version of the reaction. So don't take these reactions as literal, but they tell us how much energy we get to form, we either get or are required to form a certain compound. The standard enthalpy of formation of a single element in its elemental form is always 0. The formula for this is similar to our formulas looking at breaking and forming bonds. In this case, we're going to sum up all of the enthalpies of formation for our products, and then we're going to subtract the sum of our enthalpy of formations of our reactants. So this is Appendix L in the 9th edition of our COTS textbook. There's also a PDF of this table because it's 8 pages long, located in our class resources folder on Schoology. So our first example is looking at calcium carbonate solid decomposing into calcium oxide solid and carbon dioxide gas. So it's products minus reactants multiplied by their coefficients. So all coefficients are 1, which makes this easier. So we've got calcium oxide solid, carbon dioxide gas, add those together, and then subtract calcium carbonate solid. So these values you'd look up in the table. So you'd look up the enthalpy of formation for the calcium oxide, the carbon dioxide gas, and the calcium carbonate solid. Make sure to pay attention to the states because the states can impact what the values are. So if there are enthalpies of formation for solid, liquid, and gas, you'll want to make sure that you're using the correct state. And so once you add those together and then subtract products minus reactants, you end up with 179 kilojoules per mole of reaction for this decomposition. Our next example is nitroglycerin, which is a powerful explosive that forms 4 different gases when detonated. So there was a typo in my original question. I forgot to put the gas symbol in for water, but our question says it forms 4 gases. So it's 2 moles of nitroglycerin decomposes into 3 moles of nitrogen gas, a half mole of oxygen gas, 6 moles of carbon dioxide, and 5 moles of water vapor. Calculate the enthalpy change that occurs when 10 grams of nitroglycerin is detonated. The standard enthalpy of formation for nitroglycerin is negative 364 kilojoules per mole. So there are 2 parts to this question. The first thing that we need to figure out is the enthalpy for the reaction. And so this is where we're going to use the sum of our products minus the sum of our reactants. So copying in the 3 moles of nitrogen, half mole of oxygen, 6 moles of carbon dioxide, and 5 moles of water. And then subtracting our reactants, which is 2 moles of nitroglycerin. So all of these values we can look up in the table, except for nitroglycerin, which is given to us in the problem. So nitrogen and oxygen are both 0 because they're the elements in their elemental form. Carbon dioxide is negative 393.509. And water, make sure you look up the number for water vapor or water gas, which is negative 241.83. And then nitroglycerin we were given in the problem. So plug all of your numbers in, calculate them out. You'll do your total products minus your total reactants. So I broke apart all the numbers just so you could keep track if you're doing this along with me. So you end up with an enthalpy of negative 2,842.204 kilojoules per mole of reaction. So now the question specifically asks what happens when you detonate 10 grams. So now we have to take the 10 grams into account. So we're going to convert our 10 grams of nitroglycerin into moles. So 1 mole of nitroglycerin has a mass of 227.1 grams. And then for every 1 mole of reaction, we're going to use 2 moles of our nitroglycerin because it has a coefficient of 2 in the reaction equation. And then our enthalpy change in kilojoules per mole of reaction is negative 2,842.204 kilojoules per 1 mole of reaction. Which gets us overall negative 62.6 kilojoules of energy for 10 grams of nitroglycerin.